Okay, now that we've learned about strong and weak acids and bases, we're going to do some practice pH calculations. We're going to calculate the pH in the chloride ion concentration in a 2.56 times 10 to the minus 3 molar solution of HCl. This is a strong acid. You know this because it is one of the 6 strong acids that you learned. It's a short list given here: HCl, HBr, HI, HNO3, HClO4, and H2SO4. So that's one way you're going to know, is if you just know that list, or it won't be on your Ka table. So if you don't have a Ka, then you know it's probably a strong acid, right? So strong acids completely dissociate. So when I write the acid dissociation reaction for HCl, I just split apart the H and the Cl, and that means whatever my concentration of HCl was, it is now gone to 0 molar, and that means that at equilibrium, my hydrogen ion concentration is going to be 2.56 times 10 to the minus 3. The pH is the negative log of that number. Negative log of 2.56 times 10 to the minus 3. You plug that in your calculator, and you should get 2.59176. Now our significant figure rule for logarithms is that 2.56 times 10 to the minus 3 has 3 significant figures, which means you're going to have 3 digits after the decimal point, which is called the mantissa in a logarithm. The 2 is called the characteristic, and it has nothing to do with significant figures. So 2.592 is our pH, and the chloride ion concentration is just equal to whatever the original concentration of hydrochloric acid was, because it completely dissociates. Now we're going to move on. We're going to do 2.1 molar aqueous solution of hydrofluoric acid. Hydrofluoric acid is not on our list of strong acids. It is a weak acid, and you're going to know that because it's going to be on the table for Ka values. So you're going to look at the table, and you're going to look up the Ka. Hydrofluoric acid is near the bottom, right down here. 6.8 times 10 to the minus 4 is Ka. That's actually a relatively strong acid for the weak acids that are on the table. So when we write that one, we're going to have it partially dissociate. That's why we have the double arrow. It means we need an ice table, because we need to figure out what is the hydrogen ion concentration at equilibrium. And we're going to plug that into this expression for pH. pH equals the negative log of H plus. So we're going to start with an ice table. We need to figure out what H plus is. We're going to put 2.1 molar in for the initial concentration of HF, 0 molar for H plus and F minus. We're going to lose some value X of HF, and we're going to gain the same value X on the right-hand side for both products, which means our equilibrium expression for all of them is 2.1 minus X and X and X. We're going to plug them into the Ka expression for hydrofluoric acid, which is given here. Once we plug those in, we will have an algebraic expression. X squared divided by 2.1 minus X equals 6.8 times 10 to the minus 4. And then we need to solve for X using our favorite mathematical principle called algebra. Yay, algebra! So if we rearrange this expression, we get the quadratic x squared plus 6.8 times 10 to the minus 4x minus 1.428 times 10 to the minus 3. This is the value I got when I multiplied 2.1 times this value. So I basically moved this binomial expression over to the other side, and I already multiplied them together, right? So I combined the step of multiplying both sides by 2.1 minus x. I combined that with multiplying that binomial by this 6.8 times 10 to the minus 4. So I combined 2 steps into one between this first expression and the second expression. And then I just rearranged this expression to be in the form of a quadratic so that I can use the quadratic equation. So A is 1, B is 6.8 times 10 to the minus 4, and C is negative 1.428 times 10 to the minus 3. I'm going to plug that into the quadratic equation, and I get 2 roots for x, 3.745 times 10 to the minus 2, and a negative value, which I'm going to take away and say it can't be negative. pH is the negative log of x, which equals 1.4265. And that's going to round to 1.43. It's going to have two sig figs after the decimal point, and that goes back to the quadratic equation. You'll have to go back and figure out with each step how many sig figs it should have. I can help you with that if you need help with that. Calculate the pH and the calcium ion concentration in a solution of calcium hydroxide, which is a strong base. Another important little tidbit is that calcium hydroxide will dissociate into 2 moles of hydroxide ion for every 1 mole of calcium hydroxide. So that means that you actually form 1.156 times 10 to the minus 3 molar hydroxide ion. POH is going to be the negative log of the hydroxide ion concentration, and that's going to give you 2.93704. pH is 14 minus that number, 11.06. It's a high number, which is good because calcium hydroxide is a strong base, and so you would expect it to have a pH greater than 7. If we go back to the previous answer too, it's good that we had a pH less than 7 because hydrofluoric acid is a weak acid. You should always kind of verify that your pH is sort of in the range where you expect it to be. In this case, we have 2 digits after the decimal point here, and the reason for that is because if you go back and think about significant figures, 5.78 times 10 to the minus 4 molar, that has 3 significant figures, which means this number will have 3, 1.1, which means this number should have 3. Actually, I think this should be 11.063, not 11.06, because we have 3 sig figs originally. Oops, made a mistake there. Next, we're going to calculate the pH of a 0.50 molar solution of pyridine. This is a weak base. This is on the KB table. Pyridine is down here near the bottom, C5H5N, 1.7 times 10 to the minus 9. Relatively weak for a base. I'm going to write the base dissociation reaction. This is the hardest part of weak bases. You're going to add water, and then you're going to transfer the hydrogen ion from water to pyridine in this case, which is going to form C5H5NH+. This is the conjugate acid of pyridine. And then water is left as hydroxide. So remember that hydroxide, this is the reason why this has a high pH in the first place. It's the reason it's a base. So we're going to set up our ice table. We're going to ignore water because it doesn't appear in the equilibrium expression. I'm going to plug in 0.50 molar for the base and 0 and 0 on the right-hand side for the 2 products. I'm going to write our KB expression. And then we're going to use minus x. We're going to lose minus x on the left. We're going to gain x on the right, which is going to leave us with 0.50 minus x for pyridine and x for the 2 products. We're going to plug those into our equilibrium expression for KB to get an algebraic expression, and we're going to solve for x. We get x squared divided by 0.50 minus x equals 1.7 times 10 to the minus 9. At this point, we're going to assume x is negligibly small compared to 0.50. That will simplify the algebraic expression. You can certainly continue on and use the quadratic equation to solve for x. That would give you 2 perfectly correct roots for x, and only one of them is possible because one of them will end up being negative. However, it does simplify the algebra to make this assumption. And we'll talk later about how you'll know if that assumption is valid. So if we make this assumption, then that reduces the expression to x squared divided by 0.50, because if we assume x is negligibly small compared to 0.50, then 0.50 minus x will essentially be the same as 0.50. So we've substituted our new denominator. We've just taken the x out of that value. Now when we solve for x, we get x equals the square root of 0.50 times 1.7 times 10 to the minus 9. So x is equal to 2.91547 times 10 to the minus 5 molar. That's the hydroxide ion concentration. So we're going to solve for POH is the negative log of x. And that gives me 4.535. pH is 14 minus that number, which is 9.46. Now we're going to, of course, look at it and say, okay, the pH is greater than 7. I feel pretty good because it's a base. If you go back, you can always go back and plug x back in. We didn't validate this assumption was correct, but I can do that right now. If I plug my x value in, what did I get? 2.91, 547 times 10 to the minus 5. If I subtract that from 0.50, 2.91, 547 times 10 to the minus 5, I get 0.4999708845. And so that does round to 0.50, so my assumption was fine.